density and brief unit of joules. Okay, we've actually talked about the density as an intensive property. We've talked about grams, liters, and length. So we're going to start putting the species together. So the first thing we're going to talk about is density. Density is a characteristic property and is proper physical property. It is not associated with a chemical change. It's a physical property, and it is intrinsic to stuff, and it relates something's mass to its volume. So if you look at it, density here is mass over volume, or M over V. And the units are usually in grams per milliliter or grams per cubic centimeter. So this is grams per milliliter or grams per cubic centimeter. And you'll see those done interchangeably because, remember, 1 milliliter is a cubic centimeter. So it's the same thing. Now, the thing to always keep in mind is that density is a conversion factor that relates mass to volume. Now, why is this important? Because you can go either way on that, and I've got a little more room on the next slide, so I'll show you. Now, we said density is an intensive property. So it doesn't matter how much you have of a substance, it's going to have the same density whether you have a little or a lot. So it doesn't matter how much balsa wood, it's still going to be 0.1. Okay, because we're still relating mass to volume. Now, let's talk about it a second. Typically, as I said, the units given are grams per milliliter, but you can go either way. It's kind of like a dozen. So we say that 1 dozen is equal to 12 cookies. I'm hungry, can you tell? So, but that also means that you could say 12 cookies is equal to 1 dozen. So when you look at density, and I'll pick on iron here, this is 7.9 grams per 1 milliliter. Or you can say that 1 milliliter is 7.9 grams. As long as you keep the relationship the same. Notice the number always goes with the grams, and the milliliters are assumed as 1. Now this becomes important as you work problems, but this is basically a relationship between mass and volume. Okay, and we're going to look at it as it goes. Okay, so let's look at a problem. And this one comes out of your text. You're given a coin that you were told is solid copper. You're not sure you believe that it is solid copper. If you determine the volume and the mass, is the coin copper? Well, we know that density is equal to mass over volume. So it is 112.3 grams divided by 14.114 milliliters. So when we do the math, remember we got to have a 1 in the bottom. We find out that your density is 7.942 grams per 1 milliliter. Okay? Well, we're told that this is the density of copper, so they don't match. So it is not copper because the densities don't match. Don't match. Okay, so that's an easy way to calculate density for there. Now we can look at it a variety of different ways. Okay, and as we work problems, there you can set up ratios. I'm going to start you into dimensional analysis. More about that later. But I'm going to set it up as units canceling. So what is the volume of a 4.1 gram osmium ball? Well, this Greek symbol rho, this is the symbol for density. It's like the funky P. When I write it, I make it loopy, so it looks like that. Okay? But that's a density. So we know that volume is equal to mass over, actually, I just reversed that. I'm going to erase that. Okay, density, which is our rho, is equal to mass over volume. So our volume is going to be equal to mass divided by density. And you can do it that way, but the way I like to do it is I start with what I'm looking for. I'm looking for my volume, and I always start with the amount I'm given, which is 4.18 grams of osmium. And I know that the density is given, and because I need grams in the bottom, so that's 22.6 grams per 1 milliliter, we do the math, and we find out that it is 0.1814159 cubic centimeters or milliliters, doesn't matter. Again, if we were doing significant figures, we would end up with a 0.18 cubic centimeter. Okay? So, again, you could use this technique or this technique. I'm trying to trend towards this one because this is what we're going to use later. On this one, we want the mass in grams, so we want the grams. We start with our amount, which is 37.52 milliliters. This is our amount. And remember, density is never an amount unless you're just converting factors on it because it's a conversion factor. So we know that we need our 1 milliliter is equal to 1 cubic centimeters. So we know that we want our cubic centimeters down here, which means we want our grams up here. So when we look at this problem, everything on top is multiplied, everything on the bottom is divided. So we end up with 508.396 grams. But if we use our significant figures, we would end up with 508.4 grams of mercury here in this sample. And again, we can use the density directly, grams per milliliter, or we can use milliliters per gram. Okay? So here we have a beaker has a mass of 85.2 when it's empty and 30 whatever when it contains 325 milliliters of liquid methanol. We're looking for the density of methanol. So if we're looking for the density, we need the mass and we need the volume. So we know our volume, it's 325 milliliters. So what we need is the mass. So our total, which is our beaker plus the methanol, is going to be equal to 342.4 grams. So just the beaker itself is 85.2 grams. So if we subtract the beaker mass from the beaker plus methanol, then we're left with just the methanol. If you were to do it in reverse, then the methanol plus the beaker should equal. And so we end up with 257.2 grams of methanol. So our density, again, is equal to mass over volume. And we know that. So it's 257.2 grams. Grams divided by 325 milliliters, which gives us a density of 0.791385 grams per milliliter if we were using significant figures. And again, we'll work problems with significant figures after we do them, but I want you to come back and look at these. We should end up with a 0.791 grams per cubic centimeter or milliliter. Remember, that doesn't matter unless it specifies. You give it and you're good to go. So notice that on this one, it's got a little bit more steps associated with it because you have to do an extra step to get the mass. But if you think about it, it's not hard. The beaker, you have the weight of it, then you have the weight of the beaker plus the methanol. If you subtract the beaker, then you have the methanol. And in lab, you would be doing this. So the next units associated with this section, and we will work a number of more density problems in the extra problems and as we go, but that's our basics there, are the SI units for energy. We call that joules, and work, remember, is force times distance, so that'd be kilogram per meter squared, so that's a Newton. Again, I point that out because you can get it. We don't use the force in chemistry. You know, not the Star Wars force anyway. I mean, Star Wars force maybe, but not the physics force. So we will at one point in time look at the kinetic energy of moving particles, and that is the kinetic energy of moving particles. Again, more about that later. And the units for the joule are 1 kilogram meters squared per second squared. Okay, so we use the joules a lot. The old unit was the calorie, and there are 4.184 joules per 1 calorie, etc. Now, because that's the older one, it's got a definition. 1 calorie is the energy needed to raise 1 gram of water by 1 degree C. Do you need to memorize that? No. But we will use it in calorimetry, so it will come back, but I'll repeat it then too. The interesting thing is that these are actually called little c calories. And the reason why is when you look at your candy bar and it lists so many calories per candy bar, that's actually what they call a nutritional calorie, which is, they call it a big C calorie, which is actually a kilocalorie. This is what is in food. So when they say that you have Coke Zero or Pepsi Zero, it is not 0 calories. It is 0 nutritional calories. So as long as you stay less than 500 little c calories, then you can say it is 0 big C calories. Okay? So that's how they get it. So let's say Coke Zero has 495 little c calories. No, that wouldn't work because that would round up. So 490, then that's still less than 1 calorie. That's 0.5. So that's not 1 calorie. So that's how they do that. Now, on mastering, I think I've eliminated it, but just in case I haven't, or in case you're into energy conversions, a kilowatt hour is 3.60 times 10 to the 6 joules. And this would tell you your light bulb put out energy, etc. So, biggest thing is we're going to use this conversion right here. We'll use the next line later in chapter 5, I believe. But we're going to use that one. And again, it doesn't say memorize, so I will give it to you. So if, for example, if you were eating a bag of chips, I'm all for a bag of chips. Notice that I like food. Okay? Then we're asked for how many joules are in a bag that is listed as 140 calories. Well, remember, 140 calories is a big C calorie, so 1 big C calorie is 1,000 little c calories. And we know that 1 little c calorie is equal to 4.184 joules. So when we do the math, we get 5.85760 joules. Okay. And if we were doing significant figures, we would report it as 5900. How many zeros? 1, 2, 3, 4 joules. Okay. Now, then it asks for it in kilojoules. Okay. So if we want it in kilojoules, then we would take the 59, and we'll take the 5900, which is our final joules. And we know that there are 1,000 joules in 1 kilojoule. So we end up with 590 kilojoules of energy in that bag of chips. Okay. Now, remember when you're doing this in this form, and this is called dimensional analysis, everything on the top is multiplied, everything on the bottom is divided. And you can do it all across, or you can do it one at a time. More about that as we go. So that would be the conversion between joules and kilojoules. Okay, and again, we're one of these little lanyards, chemistry put to work, solar energy, and progressive disease approaches, and then art restoration. This basically has 3 different little sections in it. It's kind of interesting, and you may want to read through it just so that you see how chemistry can relate to everyday life.